15 millimeter. And the height is 100 millimeter. And the dimension of the ball is 200 millimeter. So very simple rectangular block like you have learned in static, and I'm looking at a way to tip the ball by applying a force in the center. So it's a very classical static problem, right? Can you do that? Think you can do that? If I tell you a force that acts at the centroid of this rectangular block and give you the weight and the geometry of the block, can you find out for me what force I have to apply at the center to tip this block? How would you do that? What would you use to get to the answer of this problem? So if I have a force, something right here, I call it X, can you solve this problem? Yes?
Does friction come into account? Like, is it, if it was a smooth surface, then when you just push the block, like?
It's not smooth.
Okay.
The block is stationary and can only tip, cannot translate. Can you do that? Yeah.
When force in the left corner is 0, the normal force on the left corner will do, well, it depends on which side we're pushing.
Here?
Yeah.
Okay. When it's 0, okay. What does that
Transfer
what does that translate to in terms of something you can use to solve the problem? That's the right direction.
just some moments less than 30.
Some moment about where?
I guess that point where it's in 30.
Okay. Does everyone hear?
Bottom right.
Does everyone hear? If you don't, you're on your own. All right, so that's a static classical problem, right? You can do that. So the only trick we put for a fluid problem is this force R X is now created by a water jet. So from here, I have a nozzle hitting this rectangular plate. It's a circular nozzle, so it's spread. Kind of like that problem we just did. One stream go vertically, and again we are idealizing the whole problem. Yeah, the water will splash and get all over the place, but we don't look at that detail. Just assume it's a very smooth spreading radially. One stream go on the top in a circular manner. The bottom stream come down and go out, and then in a very idealized way backward. And the diameter and the location of the jet is right at the center. Diameter is given. What is the flow rate? What's Q stand for, nomenclature-wise? Or metric flow rate. Q, or equivalent to that, same is the velocity. How fast this jet has to be to tip this block. So you have to be careful in this case how you draw the control wall, because there's no anchoring force on the right side of this block. Do you see it? So if I draw the control wall, including the whole block and the jet, the problem is not determined. I can't do it. Okay? So what I have to do is to break it up, where I'm repeating the previous diagram for free body diagram. Static, I have this diagram, which we will discuss. For the fluid part, my control volume now becomes the edge of the water, so that I'm now only dealing with the sheet of water, not including the block. And I have an equal and opposite force of R at X in the opposite direction, because they have to, based on what I discussed over on the right, that reaction force Rx is what changed the momentum of the jet. And that's the control volume you will use to solve this problem. So this important tip on how to choose the control volume will help to put you in the right direction. Do you see the subtlety? Do you understand what I'm trying to hint you at? Question? Question, yes?
So the fact the water jet on the bottom comes back and around,
Yeah,
that like changes the momentum of it.
yeah, I haven't get to that point yet. That's the second tip that I may discuss. But do you understand the first tip, which is the way we draw the control volume? Do you understand that? Okay, now the second problem. Okay, question?
For the free body diagram, so
Yeah.
you're just changing your distributed force from the jet into a concentrated.
Exactly.
force?
That is something I'm trying to hold back to clarify, but that's being asked, so I deal with that right now. The reaction force Rx is a sum of all the pressure distribution due to this water jet impinging on the plate. That pressure is not uniform. I don't know what it looked like. It probably peaked at the center here and changes on the edges. But that whole pressure distribution multiplied by the area resulted in this R sub X. And I want to make sure we're not double counting, because when there's a pressure force here, you may say, oh, I have to account that in my momentum equation. No, that is all being now summed and represented by this Rx force. That's very detailed, that's very intricate. So I'm not double counting. Having this take care of my pressure internal to the sheet of water and the plate, all through this Rx. And that's why I diverted and go through this kind of funky dance. Do you see the, am I confusing you? You want to take a break and have a beer? Yes? Yes?
I couldn't really follow why you picked the control volume at the jet.
At the jet here? This I have no choice. For that, let me go back to this problem. If I don't include the momentum coming in, I have no way of solving the problem. What will be the alternative if I don't choose this as my inlet plane control volume? Give me another choice. Where would you pick the left face of my control volume? What would be the alternative? I don't have one. Do I understand your question? Right? My hand are bound. On the right side, for that problem, even for this one, I have a choice. But I choose the most intrinsic control volume, which is including the plate. And by doing that, I avoid dealing with all the internal surfaces and the interaction, because it's all now internal to my control volume. I can't do this here. I can't, because if I choose my control volume on this side, there's no anchoring force. There's nothing wrong with the problem. You just choose a control volume that doesn't allow you to solve the problem. But on this side, my hands are tied. There's only one control surfaces that has to include the jet. Okay? Does that help? Questions? Yes.
So when you pick a control volume, do you have to have an anchoring force available to solve the problem?
Do you have to have what?
The anchoring force?
For most problems, the answer is yes, and that's the simplest volume, control volume to choose, like this. This is a very rare exception. I do it just one problem, just to give you a taste. All right, for most engineering problems, you don't have to deal with this. Okay? And you'll see many homework to follow the control volume. By design, we want to avoid this interface. Choose the object, the plate, the nozzle, you name it, so that all that internal pressure distribution are transparent to you and you don't have to deal with it, just like this. Does that make sense? Yes?
Can't you choose a controlled volume including the weight, and then anchoring force would be the reaction of the support or the ground? And
The answer is no. Try that at home, and you know what I mean. Right?
shouldn't we be allowed to do that though?
You can. I don't think that will I don't think that will get you the answer. But you can try. You can try. Yep. Other questions? So there was the second, yes?
No, I don't have a question.
Okay, the second hint that you have to consider is, just like being asked, what happened to this jet? It has momentum. Now, parallel, well, I didn't draw, and again, you have to establish a coordinate system. What would you choose for this problem? Standard, which is X and Y. Kind of like that one. So here, unlike the other in-class problem, I have a sheet of water coming out of here, parallel to the X momentum. So the X momentum equation out will not be zero. It has something. How are you going to deal with that? Can you make some engineering estimate? You're an engineer, you're a tech engineer. Can you make an argument and tell me I can neglect this? That I can convincingly say, well, this is going to be small and I'm not going to care. Why? No clue? No clue. I'm going to give you the answer. I'll give you an answer already, just tell me why.
Oh, because
I can neglect this. Why can I neglect this? Don't give me the answer yet. I'm debating whether you should think about yourself. Yeah, you should think about yourself. Okay? And I'll give you a hint. This momentum is small. I want you to think continuity. Think continuity. And I give you more hints. Continuity should lead you to say the velocity here is very small. And you have to tell me why. All right? I'm giving you away the problem. No more hint. The rest is up to you. Okay. Questions? All right. There are more interesting problems to come. So the next momentum problem is